So far, what I would say to you is of everything that we have learned this year, what we're talking about between yesterday and today is the most important part of the course so far in terms of Physics 30. So this isn't just about working with vectors. This is about working with vectors so that you know when you get to Physics 30 and you study momentum vectors or electric force vectors or magnetic field vectors, you know how to add vectors. So we're going to be using vector addition here that makes use of what we call components. We're going to start off by finding components of vectors and then using components to add vectors. So far, to add vectors, we've encountered the following cases. We've encountered a case where the two vectors are in the same direction, correct? Now, I just looked at this file this morning, and it's going to be a click-through thing today. Apparently, I left this for a sub 1 year. If I said to you, what is 35 kilometers west plus 55 kilometers west, since the two vectors are in the same direction, you're simply going to add the numbers together. So adding the vectors here is accomplished by adding the magnitudes. And you get 90 kilometers west, right? Piece of cake. So simple, in fact, that this question doesn't even belong in Physics 30 or 20 or Science 10. It's obvious what the answer is. It's a junior high science problem, maybe even an elementary science problem. If the two vectors are in opposite directions, then you add the vectors by subtracting the magnitudes. We're still adding the vectors. It's just that if, for example, I had 35 kilometers west and 55 kilometers east, you subtract the magnitudes. You take the magnitude that's the larger one, in this case 55, and subtract the smaller magnitude, which is 35. Hopefully we know that's 20. And I label the direction as being whatever direction had the greater magnitude. Fair? Good? Okay. Again, something that is not really elevating us to a high school level. If you said to a grade 5 student, a drone travels 55 kilometers east, then 35 kilometers west, I think as long as they could read and understand the words, they would know what the answer to this question would be. If the two vectors are perpendicular, then you draw the vectors tip to tail, draw a single vector from where the tip to tail process started to where it ended. Okay. You can then use the Pythagorean theorem and trigonometry to find the magnitude of the result and the direction of the result. So if I said to you, what is this? You're not just going to look at this blindly and go, well, 35 plus 55 is 90. Because we're not adding 35 meters and 55 meters. We're adding 35 meters west and 55 meters north, well, kilometers. Okay. So this is what we draw. And I do want us to work through this one. I know that I just went through an example from yesterday at the beginning of class before we started this lesson, but I want you to just humor me and write this down so that we have something to look at in our notes if we have to look back. So you sketch that diagram. I don't know, I'm looking at this from an angle. That 35 could maybe be drawn a little bit more. It looks okay. And we know that the sum is this. This brick-colored arrow is the sum of those two vectors. And I know that that is obvious when you talk about kilometers because it's showing overall where the object ends compared to where it starts. But next year, if we're dealing with magnetic field strength, it's not going to really necessarily make sense. You'll have to say, but magnetic field strength is a vector. The rules that we use for vector addition are the rules we use for vector addition. It doesn't matter what the vectors are, as long as you're adding vectors that are the same types of vectors. You can't add displacements and velocities. So this is what we are after. How do we find that? And as I said, this is a click-through thing for me. This will be easy today for me. That happens to be the angle, and the magnitude is the hypotenuse. So you find the hypotenuse using the Pythagorean theorem. I'll give everybody a minute to do so. It's 65, right? I don't know what it is exactly as a or rounded as a decimal form, but I'm rounding it to 65. Whether it was 64 point something or 65 point something. Do we get 65 kilometers? Okay. Well, to find the angle, you're going to have to go to your formula sheet. I don't know if I mentioned this or pointed it out. Your Pythagorean theorem is there and your trigonometry is there. By the way, I really hate this. I hate this c squared equals a squared plus b squared thing. Because I look in some junior high textbooks and it says a squared equals b squared plus c squared. I always just use this for the Pythagorean theorem. There's no need to make a distinction between the two short legs of the triangle. It's other squared plus other squared equals hypotenuse squared. Anyway, going back to finding the angle, you would have tangent of theta equals opposite over adjacent. Take the inverse tan of that, and you get 58 degrees. No? Yes. And it's going to be north of west because we drew west and then we drew north. So to summarize, if the vectors are in the same direction, you just add the numbers together, and that's the right answer with the direction added. If it's in opposite directions, you subtract the magnitudes, and the direction of the sum that you find by subtracting, the direction of the sum of those two vectors will be whatever direction had the greater magnitude. And if you're looking at perpendicular vectors, this is what you do. That's the answer. Well, let me provide some context here. If I said to you that you want to add 200 meters, 14 degrees south of east, you want to add 180 meters. You can write this down if you like, but I'm not going to go anywhere with it. 47 degrees north of east, then you would, open up that kind of flow chart, and you would say in your brain, are these two vectors in the same direction? Because if they are, I can just add the numbers. The answer is no. Are these two vectors opposite to each other? The answer is no. Are these two vectors perpendicular? The answer is no. So you don't have any skills yet in how you would add these. This first part of the lesson, where we're going to talk about vector components, is going to give us the necessary tools to add vectors like this. So, in order to understand how to add vectors that do not fall into any of the above three cases we've talked about, you need to determine what we call x and y components of vectors, or what I can call horizontal and vertical components. When I say horizontal, I'm talking about east and west. When I say vertical, I'm thinking north and south. The horizontal component of any vector is the single vector that describes how far east or west the original vector points. And if you want to talk about displacement, then I'm saying how far east or west the person moves. So we're going to be working backwards here, and I'll get into more detail with that in a second. But generally speaking, instead of knowing an east and a north and finding the total, you're going to be given a single vector that is in the northeast direction, and you're going to have to find the east and find the north component. I've got this highlighted because maybe there's a typo there in your handout. Does it say, do you have the word of? I'm just asking so that I can fix it in your notes. There's no word of there? I think the word of should be inserted just to make it grammatically correct. And you probably can imagine how important I feel grammar is. Anyway, it should be of. The vertical component of any vector is another single vector that describes how far north or south the vector points. So draw the vector diagram for a displacement of 400 meters at an angle of 30 degrees north of east. So here is how I would begin to process this in my brain. I would just, and you don't need to draw this necessarily, but I'm looking at that point and I'm saying that's where I'm going to start drawing this vector from, and this arrow is pointing east. But I want to draw a vector 30 degrees north of that. So my vector is going to be in that direction. That dotted line is not necessarily part of the vector diagram. It's just a line helping me visualize things. I think even if you don't draw that whole line, it might not be a bad idea for you to lightly draw a dotted line there to indicate that that is the horizontal. We should put 400 meters on it, right? It's not just a line. It's a line that represents something. You know, it might represent next year 40 Tesla, which is a magnetic field strength. Find the horizontal and vertical components. That whole thing is the displacement. I know that weird curly bracket is a vertical kind of thing, but I'm not talking vertical here. That whole diagram is the displacement. Okay? That is a horizontal component and that is a vertical component. And that's what we need to add now to the diagram so that we can find the horizontal and vertical components. I'm not content with just saying that and moving on. What I've got in yellow is what really happens to the object, right? And the object ends at the end of that arrow. So if you walked along that line, you would end at the end of that brick-colored arrow. What I have highlighted in blue is how far east of your position you land. I know you also land north of your position, but if you look at my arms, the end of that blue highlighted vector is a certain distance to the right of where we started. And what I've got highlighted in green, what I'm going to put in green, is the vertical thing. And where we're going with this is, if we know the blue and the green, then walking east the blue amount and then north the green amount is the same as walking 400 meters in that direction. Mathematically, physically, in every sense, those two vectors, the green and the blue, added together give you the yellow. So if we want to work with the yellow, we can throw the yellow out and work with the blue and green instead. It's like saying, instead of working with the number 10, why don't we work with 2 plus 8 instead? You'd have no reason to do that with numbers, but here you do. So find the horizontal and vertical components. Everybody, this is a trigonometry problem. Here is an interesting note, though, that if you draw your horizontal first, which I've been trying to get you to do, your horizontal, which is x on the diagram, will always be adjacent to the angle. Which means your horizontal will always be found using cosine, and your vertical will always be found using sine. And if you establish a pattern that's the same all the time, you're going to be more successful. If you keep tossing a coin as to which you draw first, sometimes your horizontal will be found using sine, sometimes cosine. So cosine of 30 degrees is adjacent over 400. This is a grade 10 trigonometry question at this point. And notice I'm using cosine to find the horizontal. Sine of 30 degrees is y over 400. So in order to solve this, and just a quick note, I'm weird this way. If I would have written this instead of having it typed in a program, I would have written this. And those of you that have me for math know how picky I am about this, that things get lined up properly so that I can say, well, this is over 1. I've got numerators lined up with numerators, denominators with denominators. But that still shouldn't prevent you from being able to solve for x and y. X here will be 400 cos 30, which means times cos 30. Y will be 400 sine 30. So can you confirm that for x you get 346.5 point something meters. Okay. And for y, you get exactly 200. No problem there? Once again, and forgive me here that I know it's not exactly 346. It's 345 point something or 346 point something. But what I am telling you is this, that 400 meters, 30 degrees north of east, is equal to 346 meters east plus 200 meters plus 200 meters north. That statement, this statement here, is a fact. That's like saying 10 equals 2 plus 8. So where we started with this kind of idea today is you don't know how to add vectors that are at these weird wonky angles because they're not north, south, east, west. You don't know how to work with this type of vector, but you know how to work with these types of vectors. So work with those types of vectors instead of the one that's at a weird angle. This is where we're going. I had that all written down anyway, okay? I guess maybe this is just a summary, right? It is east and it is north, you know that, okay? Explain the relationship. Okay, I guess I just did. But we can write it down now. The x and y components added give the displacement. And don't, sooner or later, somebody's going to say this. One of you will eventually ask me this question. You'll do a question like this, and then you'll go, but 346 plus 200 gives me 546. You told us that it's supposed to give me the displacement. I'm not adding 346 and 200. I'm adding 346 east, 200 north, and I'm not getting 400. I'm getting 400 30 degrees north of east. I'm not saying the displacements add up. I'm saying these two components as vectors add to give the displacement. So rather than what I had written, I believe, was 346 meters east plus 200 meters north equals 400 meters 30 degrees north of east. Rather than writing that, I could just say dx as a vector plus dy as a vector equals d as a vector, the total, the original vector. So rather than giving you these two vectors that are perpendicular and having you find a total, you're given a single vector and you're resolving it or breaking it into two horizontal components. Okay, we can now use a vector diagram along with vector components to add vectors. So how would I add these vectors? Okay, let's just stop for a second. Are these two vectors in example 2 in the same direction? No. Are they in opposite directions? No. Are they perpendicular? Well, 135 degrees, if you watch my arm, this is the pivot point at the origin of a map or an axis. 90 plus another 45 takes me to 135. It's off in that direction. What I am trying to add is a vector that's pointing north with a vector that's pointing kind of northwest. I'm pretty sure I'm not going to show you this diagram, so I will just draw it. What you were actually trying to find is this. You're trying to find that, right? You draw the two vectors tip to tail and you want to find that, but it's not a hypotenuse. For those of you, for the one person who has taken Math 30 or Math 20, can you use the sine law, cosine law here? Absolutely. If you want to go that route, which we do in Physics 30, feel free. But this is not, typically speaking, the way we would do this in Physics 20. We do need to consider the directions and draw these vectors individually. I don't think you need to write down everything that I'm teaching, and showing you how to do things as well as what to write down. So remember that that's north, south, east, west. This is the same as 45 degrees north of west. If I go back to this, this is 90 degrees. And if I want to get to 135, I say, well, I can take 135 minus 90. I have to go 45 degrees further, which is going to be in this direction. This will be 45 degrees. This will be 45 degrees. Right? It's 45 degrees north of west. Is it also 45 degrees west of north? Yes, but I don't like west of north. Okay? Do you agree that's north? Okay? So, this is what one of the vectors looks like, and I think you should draw this. We are not going to be drawing the vectors tip to tail. We're just drawing each one separately so we can look at them. And this is the other vector. No need for an angle there. North is north. What we would like to do here is find an x and a y component of each. Because, and I'm going to get a bit ahead of myself, rather than adding those two vectors that are in the question, what we can add instead are these four vectors that are x and y's. And the reason is the blue x plus the blue y is that original blue vector. So once we find those numbers, we can ignore that original blue vector and use the components instead. What I'm saying is the sum of these two vectors is the sum of these four vectors. That's where we're going with this. So you need to find those components. Well, I've just drawn now or revealed that on that 100-meter vector, I've indicated a horizontal and a vertical component. You with me? So how do we find the horizontal and vertical components of this? Now, again, I think I had prepared this lesson this way because I was away one year and a sub was doing this. You don't have to write all this down. I'm just putting something here that you can use to help you. Cos of 45 will be x over 100. Sine of 45 will be y over 100. Finding x and y here is child's play. It better be, anyway. X will be 100 cos 45. Y will be 100 sine 45. By the way, a 45-degree triangle like this, the x and the y are equal. And you should notice that cos 45 and sine 45 are the same. So we find those two numbers. And I get 70.7 something. Throughout this entire lesson, I'm not going to worry about exact values. You should be able to use your calculator and carry all the decimals to the very end. Okay? Maybe a little later I'll show you a couple of tips and tricks with your calculator, but I'm not concerned about that right now. When you take a look at the 120-meter north vector, how do you find the horizontal and vertical? Because there's no triangle. The answer is you just, well, that's west, by the way. Oh, this is important. Don't just put 70.7. Put 70.7 west. And 70.7 north. How do we find the horizontal and vertical components, or the x and the y components of the second vector? There's no triangle. We just look at it and we go, well, it's pointing north. The entire vector is north, so the y component is 120 meters north. The x component is nothing. And we don't even want to put north or south on nothing. There's nothing there. There's no direction because there's no vector. So we do not need to use this vector of 100 meters at 135 degrees anymore. We can use those two. And I feel as though I've mentioned this idea 3 or 4 times now. It should be solidifying in your head. We do not need to use this vector. We can use these two. And that means instead of adding those two vectors I've crossed out, we're going to add those 4 vectors, which you know how to do. Those were questions from yesterday. What you would do is say the order in which I add these doesn't matter, so I'm going to find my total x first. I'm going to take 70.7 meters west and add 0 meters to it. And this is your total west. Well, it's your total horizontal, which happens to be west. I'm going to find my total y. Well, that means I'm going to add 70.7 north and 120 meters north. These happen to be in the same direction, so I'm just going to add the numbers together and get 190.7. And again, the logic of it is this, if you look up here, please. We crossed out 2 vectors and said, let's add those 4 highlighted vectors. Now what we do is we cross out those and use this, and we cross out those and we use that. So we've gone from 2 vectors to 4 vectors back to 2 vectors, but through the genius of components, the 2 vectors we're left with now are tip-to-tail perpendicular vectors, which is a problem you could have done yesterday. Admittedly, this is a math thing we're doing. We're solving a geometry problem by using right-angle triangles. So you have to add these two. How do you do it? You draw them tip to tail. And the total is this. And I would say that if I gave you that diagram and said, what's the total of the vectors, it should be a 1-minute process on your calculator. I don't know what you want to write down. I mean, you do want to find the magnitude, which is the hypotenuse. You do want to find the angle, which is the direction north of west. Give yourself a minute on your calculator and confirm that you will get 203 meters for a magnitude, and the direction will be approximately 70 degrees north of west. Now I'll give everybody just a minute. Looking around, it appears as though we're okay with that. Jackpot. That's the answer. Just help me out here. This is the final example, yes? I wouldn't see the need for another one. We want to add these vectors. What's your first step? Your first step is to go through that kind of flow chart, that problem-solving flow chart, and say these are not in the same direction. They are not in opposite directions. They are not perpendicular to each other like a north and a west or a south and a west. So we need to take these vectors and resolve them into x and y components, which I know there are some very intelligent people in the room. Some of you could probably do without writing anything down. I do not recommend that. You have to find a balance here, but without writing anything down, you open yourself up to the possibility of more mistakes. Writing everything down is a time killer on an exam. You need to find a balance. But I definitely think you need to know what these vectors look like. Right? I think writing down each vector is a minimum kind of thing. And some of you will graduate to the point where you know what to do with the 7 and the 20 degrees to find x and y components. That's fine. Just be careful. You know, I don't care on exams about you showing your work because it's multiple choice numerical response. But very few students can write nothing down and do well on an exam. If it's written, you have to show this anyway. So we want to find x and y for both, which means you need to draw, and please draw in, this is interesting. They're both north of east, north of east. That's okay. Make sure that your arrows that you draw in for your horizontal and vertical have directions on them. Because right now you can see both horizontal are east and both vertical are north. Okay, So, well, I'll give you a minute. I want everybody to find those components. Here's where I'm leaving it open to you. If you want to write down the trigonometric equation that you're using, you can. If you want to just do it on your calculator, you can. But I want you to get the right answers for x and y for both of those. So once again, I've just put them up there so that if you are finding these x's and y's, you can one by one confirm the numbers you're getting. All right, I don't know if I actually showed work up here. I'm about to find out. I guess I didn't. I don't think there's any problem with this, but I feel as though I want to just make sure that the x for the first vector, well, I'll just throw this out here. How many of you see that this is what you're doing? When you cross multiply to find a component, you're always going to be taking the cosine or the sine of the angle multiplied by the magnitude of the vector when you cross multiply. So that's your first x. Your first y would be 7 sine 20. So you know what's happening is I'm establishing a very nice pattern here for you, I hope, in that if you draw your horizontal first, this is what you do. You take the magnitude times the cosine to find x. You take the magnitude times the sine to find y. You know, knowing that it's east and north is up to you. And then, of course, you would do the same thing with 4 and 60 degrees. So is it safe to say that we're all getting those answers? All right. So what do you do now? Why did we do this? Well, we did it so we can get rid of that ugly, awkward, weird directioned vector. And instead, use these two. And get rid of this vector and instead use those two. And adding these 4 vectors should be, you know, a 2-minute process, 3-minute process. Something you could probably do, some of you just kind of without writing anything down, you could probably hammer away at your calculator and get the right answer. But officially, the total x will be found by adding those 2 x's together. You'll notice on the side board here, I have a change that I want to make for next time, and I really should have included an example here where the 2 x's or the 2 y's are not both in the same direction, right? Where, you know, if I had 60 degrees south of east, then in my next step I would have to subtract those 2 verticals. That's my only point of what I wrote there, because I saw some of you watching me. If I take my total y, it turns out to be this. And again, the big strategy or picture is that I do not want to use those 2 horizontal anymore because I've replaced them with something that's equivalent. I don't want to use those 2 vertical anymore. I can instead use this because that's equivalent to those 2 vertical. So those 2 vectors I've crossed off at the top are the same as adding those 2 vectors that I'm left with now that are highlighted in yellow. We have to add these 2. Once again, I think once you've gotten to this point in your journey, determining the answer to the question is simple. I mean, let's face it, Pythagorean theorem is grade, I don't know, junior high math anymore. You've got to be grade 8 math where you learn the Pythagorean theorem, at least, maybe grade 7, but probably grade 8. You don't really learn how to find angles with trigonometry until grade 10, but it's a skill that stays with you. I get 10 meters. And I might be being liberal with my rounding, I don't know. And I'm getting 34 degrees for that angle. And it's north of east by looking at the diagram. Or it's north of east because I drew my horizontal first, so it's vertical of horizontal. Always. If you draw your horizontal first. You don't have to. Do what you want. You know what you need to do, you know what you have to do, get the right answer. That's what you have to do. Okay, tomorrow we're going to start taking these ideas of vector addition back into the physics realm, because right now this is just about almost surveying and orienteering where we're adding vectors on a field. But we're going to be looking at applying this to velocity tomorrow. That's the answer. Let's take a look. Can you take a look on page 34, please? What have I got there? Just a couple of questions. Well, I'll tell you what. Start with those questions that are on page 34 of your unit handout. I also have page 88 of the textbook, 1 to 3. Minimum, you get 1 and 2 done from this handout. And then maybe take a look at page 88 if you have time, but beyond that, I just want you to be able to do this. This might be a perfect time tomorrow at the beginning of class for a quiz. Now, keep in mind, if I did give you a quiz on this tomorrow, and I'm almost done, I'll shut my mouth in a second, you can get to work. It would probably be something like